Assalamualaikum and very good days to Dr. Yazid. This is the presentation about the assignment that Dr. have given to us where we need to design an ECG machine using the operational amplifiers. The members for our group is presented in the screen right now where me, Muhammad Hakim, Azamuddin, Muhammad Hazim and Nash Asukan. And I will start the presentation with introduction. First, what is ECG? What ECG do? So ECG known as an electrocardiography where it's able to obtain the electrical signal from our heart muscle. With ECG, it allows us to detect something such as the heartbeat, like abnormal heartbeat or normal heartbeat, any problem that heart-related, implants, pacemaker conditions, and also heart tracking during activities such as running and cycling. But how does ECG works? ECG obtains the data by detecting the electrical signal that's generated by our atrium and ventricle during the heart pumping. The first electrical signal generated at synod atrium during the filling blood in atrium to the ventricle. At this signal, the atrium is contract and push the blood from atrium to the ventricle and cause the P wave that we see at the bottom. P wave happen during this particular phase. When the blood fills both ventricle, at the same time the electrical depolarization will flows from the AV or atrioventricle node then to the bundle of his then to the ventricle. When the electrical signal happen in ventricle, cause ventricle to contract and give us the signal shape like in the bottom QRS complex. Last but not least is when the ventricle pump blood to the aorta and T wave is generated during the ventricle repolarization. That's all from me and we move to the methodology.
Hello, my name is Muhammad Hazim. So I'm going to discuss about the methodology of our project, which is the ECG Detection System. So for the design of the system, it consists of 3 different circuits. The first one is the instrumentation amplifier circuit. The second one is the right leg drive circuit, and the last one is passive band pass filter circuit. So for each circuit, it has its own function in measuring the ECG signal. So the first circuit, the instrumentation amplifier circuit, is to detect and amplify ECG signal. Second one is the right leg drive circuit, is used to filter the interference noise and reduce common mode voltage. And the last one, passive band pass circuit, it's used to filter the signal frequencies that lies outside the range that had been specified. So in this case, the range was set to 0.5 minimum, and maximum is 100 Hz. So next, the component that had been used in each circuit was listed in the table below. So as you can see, the components for instrument amplifier is the INA 121 and 1K resistor. Next, the right leg drive circuit, it used two operational amplifier LM741 and one 10K 10 kilo ohm resistor with two 390 kilo ohm resistor. Next, the passive band pass filter use two types of capacitor with 47 microfarad and 160 nanofarad. For the resistor, which is 6.7 kilo ohm and 10 kilo ohm. The share components was used to channel power supply, one with 5 volt and another one is negative 5 volt. And the last one is the electrode, which is 3 ECG electrodes, 2 for arms and another one is for right leg. Next, the schematic diagram of the circuit. For each circuit, for the first one is the instrumentation amplifier circuit. So as we can see, it has all connection with the human ECG simulation circuit, which will be show later on. Next, we have the right leg drive circuit. The schematic diagram was drawn in the DNAT software. And the last one is the passive band pass filter. So the cut-off frequency is 0.5 for the high pass, and for the low pass is 100 Hz. And then next is the complete system. So as we can see, the human ECG simulation circuit was included in here. So this is the final design of our circuit. Next is the experimentation circuit. This one is the practical part that we design the circuit inside the lab, and we test the ECG signal using oscilloscope. So the result will be shown in the result section later on. And the last one is the placement of ECG electrode. So it has been labeled here, which parts of the arms and legs the electrode need to be placed to have the measurement of biosignal, which is ECG. That's all from me. Thank you.
Hello, Dr. Yazid. I'm Nash KIB4005. This is part of our group's presentation. So I'll be presenting the results of our circuit. So we used ETINA software at first, and we created 3 different designs. So this is the first design, where it has the human ECG simulation circuit and the instrumentation amplifier with a gain of 50. So the circuit is made of instrumentation amplifier and ECG electrodes to try and get a basic reading first. And then we move on to the simulation of the first design itself. So here we are using an output of 20 millivolt. We have 3 different outputs, 50 millivolt, 10 millivolt, and 20 millivolts, right? And then we moved on to the second design, where we add a passive band filter. So this helps limit the bandwidth of the output signal to the band allocated for the transmission itself. It has a high pass of 0.5 Hz and a low pass of 100 Hz. Let me just move this away to give you a better look at it. All right. And let's look at the simulation of the second design. So the simulation of second design, again, an output of 20 millivolts. And it looks a lot more smoother, a lot more clearer, and less faster, more realistic reading, right? And then for the final design, we added a right leg drive circuit. So we were satisfied with the results yielded, and we went with this for our final prototype. So this is our final circuit. It has a human ECG simulation circuit, instrumentation amplifier, gain which is equal to 50, a passive band pass filter, and also a right leg drive circuit. This is the simulation that we got from a 10 millivolt simulation, right? This is our final prototype design based on the circuit that we have simulated in our third design. So we have 3 different designs, and this is the final one that we chose to go with. And this is our experimentation in the medical electronics lab itself. As you can see here, based on the reading, when you compare the simulation and the real-life oscilloscope, we get the same reading, and thus it was actually a successful circuit building and also experiment for ECG. The next few videos will be a demonstration of our TINA software for the first, second, and third design, as well as its simulation. Please do enjoy the video, and that's all from me. Thank you.
So this will be a demonstration of the first design for our circuit. We use the human ECG simulation circuit and instrumentation amplifier. If we go to the info, click on oscilloscope, we click run. Okay, click on auto, and we have a few different outputs. Firstly, with for a 50 millivolt output, this is the data or oscilloscope that we get. It's a little too fast on the end. And then this is a 10 millivolt output. This is a 20 millivolt output. Yep. Next we'll be looking at the second design. Thank you. This is the second variation of the circuit. It has a human ECG simulation circuit, it has an instrumentation amplifier with a gain of 50, and a passive band pass filter. So now let's look at the simulation. We click on run, click on auto. So this is the 10 millivolt output. This is the 20 millivolt output. And yep, this is the 50 millivolt output. We now look at the final design, which will be in the next video. Thank you. We're now looking at our third design, and which is our final design that we settled on with. The circuit has a human ECG simulation circuit, instrumentation amplifier with a gain of 50, a passive band pass filter with a high of 0.5, high pass of 0.5 Hz and a low pass of 100 Hz. Also has a right leg drive circuit. Now let's look at the simulation. Click on run. This is a 1 volt output. This is a 20 millivolt output. As you can see, this will be very similar to the practical or in the real life example or prototype that we have done and tested. And this is a 10 millivolt output. Thank you.
Hello, my name is Azam, and I'll be presenting on the discussion made on our group on the project for ECG signal acquisition. So this is comparison. On the right here is the result from our group, and this is the general shape of the ECG. As you can see here, when comparing the pattern, the usual pattern of the ECG, you can see in here that it lacks it's not really refined, so they are very jagged signal form. But if we pinpoint carefully, we can see the starting here at P, and then it goes down to Q, it goes up to R, down again to S, and then to T, and then the wave move along and it repeats itself. So what we obtain here is not 100% or very refined, very smooth looking result, because due to our limitation of our circuit, but still we managed to capture the signal
and maintain its basic characteristic. So on this part, I would say that our group successfully capture the signal, but there are also several factors that limiting it from being perfect or a bad. It can be better. It can be better. Right. So now I will discuss on the noise and filter and its effect on the circuit. As mentioned before, the signal we get the signal is not very clean, not very smooth, since our circuit lack of actually the notch filter. So when we plug in to the power supply that connected directly to the power line, actually it's connected to 50 hertz. The power line have its own frequency at 50 hertz. So when we connect them, it's also included in the circuit. Therefore, if we did not remove, then the signal is also amplified. So on this part, actually, it is better for our circuit to have a notch filter, but we did not manage to assemble that in time. But if we manage to put the notch filter, it will be better. So specifically, the notch filter is aimed to remove the 50 hertz signal, which is the power line, since most of the interfering signal from the surrounding, from the light, from the electrical stuff, from the breadboard itself, we already managed to remove it using bandpass filter. But as for 50 hertz specifically, we need to remove it. But if we are to proceed with the 50 hertz removal, we also need to include after the notch filter an amplifier, since we remove quite a portion of the signal, the ECG signal. So if we amplify it will become clearer lah. And then that's it. I think the weakness of our circuit, we don't actually have a way to remove a 50 hertz noise, even though we know noise, but we did not manage to hit it. And so as for future direction, of course, we can include the design of filter. We already came across the design. We think we can pull it through if given more time, or if we have more time. So that's kind of shortcoming on our part of not be able to actually pull it off in time, because we spend most of the time to rebuild and redesign a circuit to match with the simulation and the components available at lab. So I think that's it on the signal part. Also, since part of our objective is to reduce or to produce the ECG acquisition method circuit or device using at lower cost compared to what the market have to offer, means that it's better if we have lesser component while maintaining the functionality, or how do you say, the efficiency of device. So in our perspective, it is better to have lesser component than compared to adding more component to increase efficiency. We try to make the circuit able to work with less noise. In this case, the problem is noise, so we focus on less noise. Therefore, to go with it, I think it is better if we can just provide a room with lesser electronical appliances or working device, so that the chances to the noises to mix with the ECG signal from the subject or the patient is reduced, rather than just producing more and more filter and amplifier. So in our perspective, that will be quite money saving for our case. But again, of course, if we are to make it a real product, we have to increase the filter. But I think, yeah, that's it for me. To conclude, for this part of discussion, the problem is we don't have notch filter because we didn't manage to make it in time. So to improvise on our circuit, because there is a group that we really change information or refer to, managed to perform the addition of notch filter, and it is the signal is better, way better, although we are using almost similar base circuit. So I think that's it for me. Thank you.
Hello, Doctor. So, in conclusion, we were able to utilize the TINA software to create and simulate our function before actually going to do the final prototype. And this helped us a lot because it saved us a lot of time, as well as got us to identify and play around with different components. Secondly, we were able to use different sensors, experiment around with different transducers and amplifiers to create the best sub circuit for the electrocardiogram that we were creating. And lastly, we were able to work together as a team and also brainstorm the best possible circuit that we could create for our circuit and our assignment, so that we get a working and satisfying, as well as a circuit that would result, and in the end it did result. So that's all from us. group with Azam, Hakim, and Hazim. Thank you very much.